Question number 4 now. 4 BGT switching devices are used in H-bridge configuration, I think as in the figure here, together with 4 Schottky diodes. So we have parallel Schottky diodes. And when it says Schottky, that means the forward voltage is very small. Now to regulate the current in the load shown below, and we have now inductive load. Switches Q1 and Q4 are switching with a duty cycle of 30%. Remember now. Now Q1 and Q4, they are switching with delta equal 0.3. Okay? So when we switch off Q1 and Q4, okay, now it's the time for Q2 and Q3 to switch on. If it mentions anything about dead time, we will consider it. If it's not mentioned, so we will consider there is no dead time, okay? So now for Q3 and Q4, it will switch by 1 minus delta, which is 0.7, okay? So this is the first thinking about the question. Now switches 1 and 4 are switching with duty cycle of 0.3. The inverter has a frequency of 50 kilohertz. So the frequency here is 50 kilohertz. Delta equals 0.3. 1 minus delta equals 0.7. This is for Q1 and Q4. If you want to calculate the average and RMS values, we will use this delta for them. And also for number 3 and 4, number 3 and 2, sorry, this is 2, okay, it will be 0.7, okay. Now, what is the total loss in all the devices? All the devices means switches, means transistors and diodes, okay. So now let's analyze the circuit and see where is the current going through switching on and switching off the transistors, okay. So now we will start with Q1 and Q4, and we will switch it on for 30% of the period, okay. So now let's go and see this now on, okay, and this now will be on, okay. The current will not go through the inductor in that direction, because the question is giving us the current direction that this inductive load is maintaining, okay. So I can say this is a heavily inductive load, and we can model it as a current source, and the current is pointing from right to left, okay. So now after looking at this direction, that means our transistor Q1 and the Q4 will not be able to conduct in that direction. So what will happen? Are they able to conduct that current in the reverse direction? The answer is no. That means Q1 and the Q4 will not be conducting, and this is very important decision to have, okay. Q1 and the Q4 will not be conducting, because the direction of the current can't flow in these two transistors backward. But where the current is going to flow, it will go to flow through this diode and will come out from that diode, okay. So by this way, I maintain the same direction, and also during Q1 and Q4, we don't flow the current through them, because if they are MOSFET, yes, we can, but because they are BGT transistors, the current doesn't flow from emitter to collector, okay. But it has another way, and I think I explained that in the lecture, and there is here a practical question about this. Okay, so now we have conduction losses for D1 and D4. So let's now write this one. For D1 and D4, we are conducting during the first 30% of the period, okay. No dead time, and after finishing Q1 and Q4, now we have to switch Q3 and Q2, okay. And I think Q3 is able to conduct through that transistor, okay, and will go to the same direction, and then will go through Q2 to complete the circuit. So we have Q3 and Q2 will conduct during the 1 minus delta time, okay? And we have D1 and D4 will conduct during the delta time. That's it. I think we covered the whole period. Now we know which switch will be conducting during the delta and 1 minus delta. What about D3 and D2? D2 and D3 will not accept inverse direction of the current, so that current will not go through them, okay? And that's why they are not conducting. So Q1 and D4, Q4 will not be conducting, and also D2 and D3. D2 and D3. That's it. So the conduction losses for Q1, Q4, D2, D3 equals 0. Okay? And what about the switching losses for Q1 and the Q4? We know there is no conduction losses for them, but what about the switching losses? The switching losses also will be 0 because there is no current going through them. But I will tell you, there is a driving losses here. So there is current going there, but because the question didn't give us any information about the driving currents, so we will ignore this. So we will assume for this question that because there is no current going through DC transistors Q1 and the Q4, so also the switching losses for Q1 and the Q4 also will be 0. Okay, so we finished that, and we decided that because we understood how the current will flow. Okay, so now what is the remaining? We have Q2 and Q3. Q2, Q3, we have switching losses and we have conduction losses. Okay, and we have for D1 and D4. D1 and D4. We have conduction losses. Okay, I think we can calculate each of them by knowing the average and also the RMS values for the conductions, and by knowing the other parameters for the conduction. So for the switching losses, I think this is inductive load. That means we have to divide by 2. Okay, and because we have 2 transistors, so I will multiply this by 2 as well. All that will be multiplied by 2. So what is the Vmax? I think we have 400. We have 400 volt here times I max, which is the 5 ampere, times the frequency, which is 50 kilohertz, times the turn on and turn off time, and these are given here, about 200 nano and 300 nano, so it will be 500 nanosecond. Okay, so that will equal 50 watt. Okay, for the conduction for DC transistors, I think we know the VCE set. Okay, so we have here VCE set is 0.85. So VCE set 0.85, and again we have multiplied by 2. Okay, because we have 2 transistors. This is VCE set. We multiplied by the average current, and the average current here is the 5 ampere times the on time. Is it delta or 1 minus delta? We will see. For Q2 and Q3, okay, the conduction time is 1 minus delta. So we have to multiply just by 1 minus delta, which is 1 minus delta is 0.3, so it will be 0.7. Okay, 1 minus delta is 1 minus 0.3. Okay, and that's it. So the answer will be 5.95 watt. Okay, now let's go for the conduction dissipation for the diodes. I think we know it's V times the average current plus, if we are given the resistive value for the diode, so we multiply it by the RMS value for the current. Okay, so again we have the VF times the average value plus the RF times the RMS value square. Okay, and the VF equals, we have the VF to be 0.3 times the average current is 5 times the on time of the diode. Okay, D1 and D4, as mentioned here, they are conducting during delta. Okay, so it will be 0.3 plus RF, which is 10 milliohm, times RMS value square. So this is the square. RMS value is 5 times square root of 0.3. Okay, so that will give us answer of 1.05 watt. So in total, we have these powers, which is 50 and about 5.95 and also 1.05. Altogether will be 50 plus 5.95 plus 1.05, and altogether will be 57 watt as power loss. Okay, let's go now to see what is the remaining of the question. If now all devices are mounted on a common heat sink and required to be kept below 60 degrees and the ambient is 25, what is the thermal resistance? Again and always, R thermal equals the difference in temperature divided by power dissipation, and we have 60 minus 25 divided by power dissipation, which is 57, and that will equal 0.614 Celsius for each watt. Okay, so we can select a heat sink with thermal resistance 0.6 or 0.4 or lower than. If we couldn't achieve that, we can use heat sink with fan or with water cooling system. Okay, so this is for this question, and I think we finished that. Okay, let's go now for problem number 5. The BGT are replaced now with 4 MOSFETs. Okay, and remember, MOSFET can conduct in a forward and in reverse direction as well. Okay, it's not like the BGT. Now, with the characteristics given below, and these are the characteristics, what is the new power loss, total power loss? Okay, again, for the switching transistors and also for the diodes. Again, we have, I think, the same delta from the previous equation, which is the delta was 0.3, 1 minus delta will be 0.7. We want to know which will be conducting during delta and which will be conducting during 1 minus delta. Again, we have Q1, okay, and the Q4 will be conducting first, okay, and because the current is going in that direction, okay, that means it should go through the diode or through the transistor. And because here we have that transistor can accept reverse flow, so I think it will go through the transistor now. We will assume that while the current going through that transistor, it will generate some voltage here. Okay, we will assume that voltage, which is, I think, I times R ds on. Okay, that voltage is less than the voltage needed to turn on this diode, because that diode, if you want to turn it on, just apply across its terminals voltage more than the forward voltage, which is here 0.3. Okay, and because RDS on here is very, very small, so if I multiply it by also high current, the voltage will be also very small and will not turn that D1. Okay, because if you turn it on, the current will flow through D1 as well and might share it with the MOSFET. This is impractical. Okay, so we will assume that D1 will not conduct if the MOSFET is conducting. So Q1 and Q4 will be conducting during delta time. Okay, and it will be conducting like this. So we have this flow of current, okay, will be like this through the Q1 and Q4. We don't have dead time, so they will switch off. And during the switch off now, we are going to make Q3 and Q2 on during the 1 minus delta. So we have Q2 and the Q3 now will be conducting during 1 minus delta. Will they maintain the same direction or it will go through their diodes? I think we will check that by going. So let's see. Yeah, it can conduct in that direction and will go like this, and it can conduct in that direction. So Q1 and the Q4 will be conducting during the delta time, and the Q2 and the Q3 will be conducting during the 1 minus delta time. Will the diodes be conducting? The answer is no, according to our analysis. Okay, so now the first thing is the power conduction or losses for the diodes equals 0 watt, because they will not conduct during the on time or off time. If we have dead time, yes, they will conduct. Okay, so now we have 4 switches, which are the MOSFETs. They will conduct and switch. Okay, and for that we have now 4 switches. Okay, Qs, Q1 to Q4, and they have power switching losses and also conduction switching losses. So the switching losses is similar for all MOSFETs because they are not dependent on delta. Okay, so I can really say we have 4 switches times, what is the Vmax? Vmax is 400 here. Okay, times Imax, which is the 5 ampere, times the frequency 50 kilohertz from the previous question, and T on and T off we have here 100 nano and 200 nano, 300 nano, divided by, we have inductive load, so it's 2. Okay, and the answer will be 60 watt. Okay, now for the conduction we have 2 sets of transistors. 2 of them, they are switching on at delta, which is 0.3, and other 2 switching on at 0.7 of the duration. Okay, that means we have different average and RMS values for each of them. Okay, let's now calculate. For Q1 and the Q4, we have I average and IRMS. I average equals the 5 amp, we have 5 amp times delta, okay, which is 0.3, and that equals 1.5 ampere. Okay, and for the RMS we have 5 ampere times square root of 0.3, and that will give us 2.74 ampere. Okay, now this is for Q1 and Q4, but for Q2 and Q3, the average and RMS equal, we have 5 times 1 minus delta, so it's 0.7, so 5 times 0.7 will give us 3.5 ampere, and for the RMS it's 5 times square root of 1 minus delta, which is square root of 0.7, and that will give us 4.18 ampere. So be careful if the delta is different for switches, so you have to calculate the conduction losses for each in different way. So what is the conduction losses for this set and for this set? We have conduction losses here and also another conduction losses there, and the conduction losses is RDS on here, so we will use the RMS value square for that. So we have RDS on times I square RMS, and the same for this one. okay, and I think the RDS on is 0.002 ohm. So we have here 0.002 times 2.74 square, and this one is 0.002 times 4.18 square. And again, we shouldn't forget that all this should be multiplied by 2 because we have 2 transistors, and this one should be multiplied also by 2 because we have 2 transistors. Okay, so the first one, the answer will be 0.03. The second one, the answer will be 0.07. Okay, so now in total we have maybe different power dissipations. We have the diodes 0, we will not count it. We have the switching losses for the 4 switches, 60 watt, but the conduction losses for the first two, 0.03, and the second two, 0.07. So I think the total power loss equals 60 plus 0.03 plus 0.07, and that will give us 60.1 watt. And this is the answer for question number 5. And now let's go to question number 6. And in this question, we have the time. That means we should be understanding the flow of current during the on time and off time and during the dead time, and which of these switches will be conducting to calculate the average and RMS value for that. Okay, so the same circuit, the same current, the same inductive load, and we will see now which one will be turning on and off. Okay, so to prevent, it says here, to prevent the shoot-through while switching, and we know shoot-through is where we have, for example, Q1 and the Q2 are switching on together, overlapping, and that will make short circuit, and that might damage or heat our switches. Okay, so to prevent that, we will provide the time. So the MOSFETs are equipped with gate drivers, and these gate drivers provide a 5% dead time. Okay, so we have, for example, the first switch is on and off, and then will be on and off. Okay, the second switch here is off, and before turning on, it has to wait small dead time. Okay, and then will turn on, and here we have turn off, and before the other one turn on, it has to wait also small dead time, and this will be off. Okay, so we have here duration number 1, we have here duration number 2, and we have here duration number 3, and we have duration number 4. Okay, so we will know where the current is flowing through all these periods. Okay, now what is the power dissipation in each device? In each device means switches, MOSFETs and diodes. When diodes with the following data are used, given that Q1 switches with duty cycle of 0.3. Again, Q1 and the Q4 will have delta as 0.3. Okay, and Q2 and the Q3, they are supposed to have delta as 0.7, but the question says you have to provide 5% dead time. Okay, so if Q1 and the Q4 are switching as 0.3, so we have here 0.3 of time. Okay, and the dead time here is 5%. That means this dead time is 5%. Okay, and other dead time here, it is another 5%. So we have another 5%. What is the remaining time for the Q2 and the Q4? It will not be 0.7, it will be 0.6. Okay, so again, we have dead time here, delta equal 0.05, 5%, and another dead time and that will be another delta 0.05. I call all of them delta, but I should, I think, give delta and delta prime for Q2 and Q3, and delta double prime, for example, just to differentiate them from each other, okay, for the time, okay. So, okay, we know the dead time and Q1, Q4, Q2, and Q3 duration, but we don't know which switch will be conducting during the first 0.3, during the second 0.05, during the third 0.6, and during the fourth 0.05 periods, okay? And this will be investigated now, okay? So again, the delta is 0.3, and the inverter has frequency of 50 kilohertz, okay? Okay, now the MOSFET has RDS on as 0.1, which is very high, and that concerns me, because if there is current going through that 0.1, it might develop voltage across it that will turn on the parallel diode. So for example, if there is current now, we'll go through that Q1, okay, that 5 amp now, let's see, okay, we have 5 amp. If I multiply it by the RDS on, once I switch on Q1, it is 0.1, that will give us 0.5 volt across my MOSFET, okay, and it will be across my diode. Now the question, will my diode turn on or no? To know, we have to know the forward voltage, and according to the information here, we have forward voltage of 0.3. That means yes, it will turn on and take all the current, and we will assume it will take all the current. Practically, it might take partial current, okay? But here we will assume that it will take all the current and will not leave anything for the MOSFET. So the MOSFET will switch on Q1 and pass the current, and then will develop voltage, will turn on the parallel diode, and the diode will take all the current later. That means the first stage, yes, Q1 will switch on, okay, but the conduction will be not through the Q1, it will be through the diode, the D1, okay? So 0.5 voltage across that MOSFET will turn on the diode, and the conduction will be through the diode, not through the MOSFET. And that give us more accuracy about how we calculate the conduction dissipation, okay? The power dissipation through the conduction. Okay, now let's analyze the circuit. Again, we have a Q1 and a Q4 will be switched on as a first, okay? So the current will flow like that through Q4, and then the same direction of the load current, and then will go up. But as I said, once they switch on, so we have paid some power to switch them on, okay? Once they switch on Q1 and Q4, they will develop voltage, but the conduction will be during D1 and D4. So now we have switching losses for Q1 and Q4, okay? But the conduction gone through D1 and D4. And what's the period? The period is 0.3. During the delta was 0.3 for them, okay? Now we finished 0.3, 30% of the period, and now we will wait for 5% dead time. During the dead time, we are switching off all the transistors. That means Q1 and the Q4 will be off. But again, the inductive load continues pushing that current. And now the current, I think, is already established its route to go through that diode and to pass through that diode, okay? From the first 30%, it's already going through the diode. And when you provide the dead time, it will keep going through the same diode. So we have D1 and D4 will work during the 0.3, okay, and also during the first dead time, and then Q3 and Q2 will switch on, and they will provide current like this during through the MOSFETs, and go like this and go to the other MOSFET. Okay, will it go through the diode? The answer no. D2 and D3 will be backward and will not conduct. So D2 now and D3 will not be conducting at all, and nothing will be calculated for them. So Q2 and Q3, we have switching losses for them, Q2 and Q3, and also we have conduction losses, Q2 and Q3. We have conduction losses, but the period is, let's see, is 0.6. So the delta for them is 0.6. So during the 60% of the time, they will conduct, not their diodes. Okay, now after that, we have another dead time. And during the dead time again, we will switch off all the transistors, but the current is going, still going. And the current will just find one way to go, which is through D1 and D4 again. Okay, so D1 and D4 will have another conduction losses during the second dead time. Okay, so the conduction for this circuit is just either through D1 and D4 or D2, Q2 and Q3. It's not going through Q1 and the Q4. So there is no conduction losses for Q1 and the Q4, and no conduction losses for D2 and D3. Okay, so Q1 and the Q4, no conduction losses, but there is switching losses. Okay, why? Because as mentioned, the parallel diode will not turn on until the current goes through the MOSFET. So we have little bit of conduction losses, but it's ignored, but we have switching losses. I will add something here. Okay, during the switching on, yeah, we dissipate some power. Okay, but during switching off Q1 and the Q4, there is no power dissipation, but I will ignore this point. Okay, why? Because there is no current going through Q1 and the Q4 before turning them off, because all the current is going through the diode. But we will ignore that because all these just approximated calculations. Okay, so now let's calculate the switching losses for 4 transistors. So it's 4 times, what is the voltage maximum? It's 400 times I maximum 5 ampere times the frequency 50 kilohertz, and times the on time and off time about 300 together nanosecond. Okay, divided by its inductive load, so it's divided by 2, and that will equal the 60 watt again. Okay, so we have this value. Now for the conduction, we have D1 and D4. For D1 and D4, we have to calculate the average current and RMS current. Okay, so I average and I RMS will equal. I average is 5 times the conduction time, and the conduction time is 0.3, 30%, because it's not going through the MOSFET, it will go through the diode, the first 30%, and then during the dead time number 1 and dead time number 2, we have also flow through these diodes. So in total, they have 40% time. Okay, so that's why we will say it's delta 40%. Okay, and that will equal 2 ampere. Okay, and the RMS value is 5 times square root of the 40%. That will equal 3.16 ampere. Okay, so this is the conduction for D1 and D2, and we just calculated the average and RMS value. But for the conduction losses, it equals the VF times I average plus RF times I RMS square. Okay, and that give us what is the average forward is just 0.3 times the average current is 2 plus 10 milli times 3.16 square, and that will give us a value of, and please don't forget that all of that should be multiplied by 2 because we have 2 diodes here, okay? And that will equal 1.4 watt, okay? So if you forgot to multiply it by 2, that means you just calculated for one diode and you have to add the same amount for the second diode, okay? We have 2 diodes here, okay? So again, for the power conduction, for Q, we have Q2 and Q3. So we have to calculate the average current again, and the RMS current. It's 5 times delta. What is delta for Q2 and Q3? Here is the delta, which is 0.6, okay? So we have to use this one. And that equals 3 ampere. For the RMS value, it will be square root of 0.6. That will equal 3.87 ampere, okay? So what is the conduction for these 2 transistors? And remember, we have 2 of them, okay? So it's 2, this is 2 just in case, and this is 2, okay? The conduction equals RDS on times IRMS square, and that equals 2 times RDS on is 0.1 ohm. We have here RDS on as 0.1, and the RMS value is this one, which is 3.87, and after multiplying by 2 it will be 3 watt, okay? So now, by looking at all the dissipations, we have for the conduction we have this value for the transistors, and we have this value for the diodes, and for the switching we have that value for all the transistors. So we have P total will be 60 plus 1.4 plus 3, and that will give us 64.3 watt, okay? So I think we finished this question. And yeah, there are some assumptions in this question, and we assumed, for example, that once we turn on the parallel diode, all the current will go through that diode, but practically it might share it. And I will show you now just an example as addition. You don't need to calculate that. So if I have here a MOSFET, and that MOSFET has already a diode parallel to that, okay, as external one. So it's not the internal diode, it's the external one. And in the question, we said that there is current will go from there and to go to the MOSFET upward like that, and it will develop voltage between that point and that point, okay? We have current of 5 ampere, okay? And RDS on was 0.1, okay? So the voltage developed across that MOSFET was 5 times 0.1, and that equals 0.5 volt. Now, when we develop that 0.5 volt between that point and that point, the VF for the diode was 0.3. That means it will turn on. But we assume that all the current will go through the diode. But in reality, that is not practical, okay? We have some current going through that diode and some current going through the MOSFET. But how much going through the MOSFET? To know that, once we turn on the diode, that diode will drop voltage across its terminals equals to 0.3. So actually, we have that voltage between that point and that point will equal 0.3 volt, caused by the diode, or maintained or regulated by the diode, okay? So if you have 5 ampere coming from there, we have 5 ampere, how much current will go through the transistor and how much will go through the diode. So to know how much will go through that transistor, we know there is voltage, positive and negative, and there is resistor here. This is the drain and source, okay? And there is current going through there, okay, which is 5 ampere, okay? That voltage is 0.3, and we know the resistance, which is 0.1. So the current equals 0.3 volt divided by 0.1 ohm, and that means 3 ampere. 3 ampere will be going through that transistor here, okay, and 2 ampere will be going through that diode. This is more accurate answer, okay, but you don't need to go through this if you are looking for some assumptions, like you assume that all the current will go through that diode, but practically this is what happens, okay. And if you have chosen forward voltage across the diode lower and lower and lower, yes, you can reduce the current going through the MOSFET. And I will show you some technique. Sometimes they add another diode like this to the MOSFET, and the parallel diode, it comes from that point to that point, okay. So they don't add parallel diode only, they add another series diode just to prevent the current going through that MOSFET like this, okay. And in that case, all the current will go through the diode. That diode is called the blocking diode, and they use it for one reason: to prevent this MOSFET to flow the current backward and to make all the flow going through the external diode. Why? Because they might choose external diode that has different and lower conduction losses than the MOSFET. So in that case, they are reducing the conduction losses and the heat and maybe the size of the heat sink by introducing or by just installing one external series diode, which is the blocking diode, as extra. So these are extra information. You don't need to consider this as answer, but it's good to know. I hope you enjoyed this session, and you have to practice that by your own and see the solution later, and see you in the coming video. Thank you very much.